So today we are going to discuss Bellman-Ford algorithm. So Bellman-Ford algorithm is slightly, you can say, better than Dijkstra algorithm. So Bellman-Ford algorithm computes shortest path from single vertex. So it is usually Bellman-Ford is used in weighted digraph. It is slower than Dijkstra's algorithm for same problem but more versatile as it is capable of handling graphs in which some of the edges weights negative numbers. Okay, so some of the edges will be can have the negative numbers. So basically Bellman-Ford algorithm can deal with the negative weights in a graph. However, very important thing is that if there is a negative weight cycle in the graph, then Bellman-Ford algorithm cannot solve that problem. In fact, it can detect the cycle. We'll come to this later on. So, who has developed this algorithm? So, Alfonso Schimbel in 1955 first introduced this algorithm, but instead after Richard Bellman and Lester Ford Jr., who published in 1958 and 1956 respectively. So it is like first Alfonso has come up with the idea, and later on the publication happened through Richard Bellman and Lester Ford Jr. Based on their names, the nomenclature of these algorithms come. So what happened here? What happens here? Here, negative edge weights found in various application of graphs. This is why this algorithm is useful. That means Bellman-Ford algorithm is useful because it can deal with the negative weight. However, if a graph contains negative cycle, the things that I was mentioning, cycle whose edges sums to negative values, that is reachable from the source, then there is no cheapest path. That means in that case, Bellman-Ford cannot solve this problem. Any path that has a point on the negative cycle can made cheaper by one more work around the negative cycle. So if you continuously in a repeated fashion run through the negative cycle, then it will the cost of the whole path will get reduced and reduced, and so that will create a lot of problems. So basically negative cycle, Bellman-Ford cannot. If negative cycle is existing in a graph, then Bellman-Ford cannot solve it. It cannot find the shortest path, single source shortest path. In such case, Bellman-Ford algorithm can detect and report to the negative cycle. But however, if the question is asked whether Bellman-Ford algorithm can detect a negative cycle, the answer is yes. So what is negative cycle? In this graph, you can see that S is a source node, and it has, this is -1, this is -2, and this is +2. So -1 plus -2, which is -3, +2, which is -1. So this graph is having a negative cycle. So this kind of cycle can exist in a graph. Okay, in this case, Bellman-Ford cannot find the shortest path, single source shortest path. Okay, so Bellman-Ford can detect negative cycle, however it cannot find the shortest path, the total path. But in this case it is okay. Minus, in the second figure you can see that -1 plus 2 plus 2, that means 2 plus 2 4 minus 1, which is 3. In this case the cycle exists, but it is not a negative cycle. So this kind of cycle is perfectly fine with the Bellman-Ford. So Bellman-Ford follows dynamic programming approach. This is also an interesting thing. Sometimes question being asked whether Bellman-Ford followed dynamic programming strategy. Answer is yes. However, Dijkstra algorithm is bit like greedy method, and it uses priority queue, if you remember, and also sometimes mean heap data structure. However, Bellman-Ford can be implemented through arrays. Okay, now let's see how things happen. So like Dijkstra algorithm, here also in case of Bellman-Ford, relaxation concept is used. So what is relaxation? Let's say this is u, this is v, and initially this vertex v is infinity, and this vertex also is infinity. So this distance, let's say it is 7. So initially if it is 7, then infinity will be overwritten by 7, and then this infinity will be overwritten by 2, because u to this vertex x, let's say distance is 2, so after infinity it will be 2 only. After infinity this will be 7 only, because this weight, this edge weight is 7. And then finally you can say that u to v weight distance is 7. However, later on you can explore this x path, which is again connected to v path, which is again connected to. So here you can see that from x, which is a node in between this u to v, you can say once this node x has been discovered, then you can find that you can visit vertex v from u via vertex x, which will be having 2 plus 3 5. So 7 can be overwritten by 5, and because you get minimum path compared to the previous distance, that means u to be earlier distance was 7, but once you discover x, you end up getting a path cost of 5. So this concept is called relaxation concept. That means finally we relax this u to v edges and we follow this path. So initially du is infinity, then it has been initialized to 7, and direct distance from u to v is 7. Later on, with vertex x is being discovered and its distance become 2 from the vertex u. Therefore, via vertex x, the dv becomes dv equal to 2 plus 3, which is 5. So 7 will be overwritten by 5 because 5 is less than 7. So this concept is called relaxation. Which one we are relaxing? We are relaxing this path. We are relaxing this path. Okay. Now, so the relaxation concept is this function. What it does? If du plus wuv, that means if you encounter a path which is having which will end up giving you less path cost, then from the previous one, then you will be choosing that edge. So you are in du, and then you encounter this wuv, let's say, which is 2 plus 3, which is 5, which is less than equal to 7 dv. Then we'll assign this 5 to dv. That means this new path 2 plus 3 will be assigned to dv. Okay, so this concept is called relaxation concept. Now, in case of Bellman-Ford, if there are n vertices, so repeat relaxation technique can be used maximum n minus 1 time. That means in case of Bellman-Ford algorithm, you have to run the loop for n minus 1 times, and n is the number of vertices, let's say. So here you can see this is our graph. This is the figure A, and figure A is the original graph. So this is the starting vertex. I have here A, B, C, D, E, F. That means 1, 2, 3, 4, 5, 6 vertex. So in the repeat relaxation, it will run 5 times. 6 minus 1, 5 times. Okay, that we have to remember. So what you have to do first, so we can see that first whatever the all edges you have to write, whatever the possible edges. In this case, let's say A is the starting vertex, which is source vertex. So all edges you have to write initially. So AB, AC, AD, then BE, CE, DC, DF, EF, and CB. These are the all edges. Okay. Now in these edges, you have to just update the weights. So from A to B, first of all, we are starting from A is the source vertex. So it is the cost is 0 here. So A to B, because first time we have this AB, so A to B is nothing but 3. So this infinity will be updated by 3. So infinity has been updated by 3. Then we have AC. Then AC means C is initially infinity. Initially all vertices will be infinity distance. So B also infinity, E also infinity distance, F also infinity distance from A, D also infinity distance from A, and C also infinity distance from A. So in this case what happens? A to B infinity distance, we will update infinity by 3, because so this is we are updating by 3. A to C, second one is A to C. A to C it is infinity, because the distance is 2, so we will be updating by 2. Then A to D, which is 4, so it will be updated by 4. We have updated by 4. Then BE, so already we have 3 here, and then minus 1. So 3 minus 1, 2. Infinity will be updated by 2. Then CE, CE. So C already infinity has been updated by 2. So CE, it will be, this age is having 3. So 3 plus 2, 5, but it is already having 2. So there is no need of relaxation concept because already this is 2. Then DC, DC is this one. So DC is already having 2, and then 4 minus 2, 2. So there is no change. Then we have DF. DF means this one. So D is already 4. This is minus 1, infinity. So 4 minus 1, which will be 3. So infinity will be updated by 3. Then we have finally CB. CB is this one. So this is 2, this is minus 1. So 2 minus 1, 1. So 3 will be updated by 1. Okay. So this is the first iteration things happen. So first iteration happens. So this is the first iteration. So how many iterations will be there? Because we have 1, 2, 3, 4, 5, 6 vertices, we will be having 5 iterations. 6 minus 1, 5 iterations maximum. Before that itself we can converge. The output we can get. Okay. The output can be converged before that. That means there is no change in the updation table. Okay, now in case of second iteration, what happens? So this is now our graph. So this is our graph. Okay, now what happens here? You can see first it is AB. So AB is 3 and this is 1. There is no need of updating this one. Let it be like this. Then AC is already 2. So there is no need of updating. We cannot get any better results. Then AD, which is already 4. So there is no need of updating. Then BE. So BE, we have here 1 here, and this is minus 1. So 1 minus 1, which is 0, but this is 2. So 2 will be updated by 0 because 0 is less than 2. Then CE is this is 2, this is 3. So 3 plus 2, 5. 5 is greater than 0. So there is no need of updating this one. And then we have DC. DC means this one. 4 minus 2, 2 already updated. There is no need of updating. And then DF. So DF is this one. 4 minus 1, which is equal to okay. So you can see here 4 minus 1, which is already 3. But then EF, when you so this is no need of updating. But when you have EF, this one already it is 0. 0 plus 2, 2. So 3 will be updated by 2. Okay. So now this is, and then CB is this one. CB is already, it is 2, 2 minus 1, 1. There is no need of updating. Now if you see this, and this is my second iteration. Now third iteration, what happens? Third iteration, any changes happens? Third iteration, it is just as it is. This is 1, this remains 2, this D remains 4, this E remains 0, then F remains 2, and this is 3. All the other edges remain same. So there is no updates happen in third iteration, no updates happen in fourth iteration, no update even happens in fifth iteration. So there is no update after third iteration onwards. So what is the cost shortest distance from the source node from A? This is the final thing. So A, it is 0, B, it is 1, C, it is 2, D, it is 4, E, it is 0, F, it is 2. This is the final distance from the single source. That means from A, this is the final distance. You got it. Now what is the time complexity? Time complexity is V into E. Big O of V into E is the time complexity. So this is the Bellman-Ford algorithm, which is very important algorithm. However, Bellman-Ford can work on negative weights, but Dijkstra algorithm cannot work in negative weights with negative weights. So if you see so Dijkstra versus Bellman-Ford, what are the differences? So you can see that Dijkstra algorithm does not work correctly if there is negative weight edge. It assumes that one node is reached with the shortest distance. That distance cannot be improved later. Cannot be improved later, which fails if there are negative weights. So Dijkstra algorithm no way can be handled, and it can handle negative weights. Bellman-Ford, however, it can do. Okay, and then algorithm type. Dijkstra algorithm follows greedy strategy, greedy algorithm, greedy method. Bellman-Ford algorithm uses dynamic programming strategy. Like paradigm wise, if you think, then time complexity Dijkstra algorithm takes O E log V, whereas Bellman-Ford O V into E. Okay, efficiency. Dijkstra algorithm is obviously more efficient than Bellman-Ford, but Dijkstra algorithm, it has to be provided as a non-negative cycle and non-negative weight. In both cases, Dijkstra will fail. Bellman-Ford will fail in negative cycle, but negative weight it could have. So this is negative weight cycle. So Dijkstra cannot detect negative weight cycle. Bellman-Ford can detect. However, Bellman-Ford cannot solve. That means it cannot find the shortest single source, shortest path if negative cycle exists in the graph. And graph type, Dijkstra algorithm works on directed undirected graph, and Bellman-Ford also works on directed and undirected graph. So if you can see the comparative study, and negative weights Dijkstra cannot handle. Bellman-Ford can handle. However, time complexity already I discussed. Negative cycle detection Dijkstra cannot do. Bellman-Ford can do. And in terms of efficiency, it is more efficient. Which one? Dijkstra algorithm is more efficient, and this is less efficient Bellman-Ford because it can deal with the negative weights. Algorithm type it is greedy. This one is dynamic programming. So in summary, Dijkstra algorithm for graphs with non-negative weights, efficiency is the key, and use Bellman-Ford algorithm when the graph may contain negative weights or you need to detect negative weight cycle. So I hope you understood Bellman-Ford algorithm. Thank you.